Okay, so today we're gonna go over 118A quiz 1 review practice. Let's go over the questions that you sent me on Discord. So let's share our screen right here. And let me know if I'm cutting off because my internet might be laggy. Am I cutting off right now?
No.
Okay. So you wanted to go over this problem right here? Draw the products of the given reaction, include all appropriate hydrogen atoms and charges. So, hello, Elysia. This problem here is asking you to draw out the product here.
Yeah.
Right? Where if you see this nitrogen atom and oxygen atom right here, those are hetero atoms, right? And do you know what hetero atoms are?
The ones that aren't like carbon and hydrogen.
Yes, the atoms that are not carbon and hydrogen. So nitrogen is a hetero atom and oxygen is a hetero atom. Do you know how many lone pairs of electrons are in this nitrogen atom here?
One.
Yes, one lone pair. What about the oxygen? How many lone pairs of electrons are on the oxygen?
Two.
Yep, two. So this is going to be an acid-base reaction because we have acidic hydrogen proton. Since this proton here is partial positive charge, do you know why these hydrogens here are partially positively charged? Like why they have a partial charge of positive, like partial positive
Because
charge?
oxygen is more electronegative.
Yep, oxygen is more electronegative. And then think of positive hydrogens on electronegative atoms as acidic hydrogens. Does that make sense? Like they are
Oh,
attractive to bases.
so if the hydrogen is partially positive, it's acidic.
Partially positive and attached to an electronegative atom. Yes, like
Okay.
these hydrogens here, right? But now we have to figure out which one's going to be our base, which is going to be our acid. So our stronger base is going to be the less electronegative atom, right? So stronger base is the less electronegative atom because the less electronegative atom is more willing to give up electrons and attack a hydrogen, right? Like the role of a base is to get protonated, to attack a hydrogen, to grab a hydrogen. It's better to do that if it is less electronegative. It is less greedy for electrons because it can donate that electrons to attack. So based on this concept right here, which atom is less electronegative, nitrogen or oxygen?
Nitrogen.
Yep, nitrogen. So nitrogen here is going to be considered our base. So the molecule on the left is our base. The molecule on our right is our acid, right? So to draw the mechanism, arrow pushing arrows, the lone pair of electrons on the nitrogen is going to attack that hydrogen right there. It's going to grab that hydrogen. It's going to make a bond between that nitrogen and hydrogen. Does that make sense so far?
Yeah.
Yeah. So when that happens, this bond right here between the hydrogen being grabbed and the oxygen has two electrons. Those two electrons are going to go onto the oxygen right there, giving it an extra pair of electrons.
Yeah.
Right. So when I draw out the product here, I'm going to draw it in bond line form. This is what I am going to get, where we have this nitrogen attached to three hydrogens now, and no pairs of electrons. What would be the formal charge of this nitrogen right here if it has 4 bonds and 0 lone pairs of electrons?
+1.
Yeah, +1 charge because nitrogen is on the 5th group, 5th column.
Yeah.
So it wants 5 electrons to itself, but it has 4. 5 minus 4 is +1. Now let's look at this oxygen right here. This oxygen has 1 bond and 3 pairs of electrons. What would be the partial charge of this oxygen here? I mean, the full formal charge of this oxygen here with 1 bond and 3 pairs of electrons.
-1.
Yep, -1, because oxygen is on the 6th column or 6th group of the periodic table, but it has 1, 2, 3, 4, 5, 6, 7 electrons to itself. 6 minus 7 is -1 charge. Right, so this is going to be the answer here. Which one's the conjugate acid? Which one's the conjugate base?
The conjugate acid is the one with nitrogen, and then the conjugate base is OH.
Minus, yeah, that's right. Conjugate acid is this NH3 plus or NH3 plus, and the conjugate base is this OH minus right here. That's right. That's the answer here.
Okay, so to determine the acid and base, the acid would be the one with the more electronegative atom.
Yes, the acid is going to be the one with the more electronegative atom, and the base is going to be the one with the less electronegative atom, in this case, in this example here. Right.
Thank you.
Mm-hmm. Is the hydrogen on more electronegative atom, right? Because the more positively charged the hydrogen is, the more is this hydrogen right here on the oxygen is more positive charge than the hydrogen here. That's because this oxygen is more electronegative, making this hydrogen more positively charged. It's pulling on the electrons more on the hydrogen, making this a bigger positive charge on the hydrogen right there, making it more acidic. Right.
Okay.
And this nitrogen here, since it's less electronegative, it's more able to attack, more able to donate electrons to attack that positively charged hydrogen right there.
Okay.
Yeah. Mm-hmm. Yeah. So, hey, Alicia, is there any practice one that you wanted to go over first, like the one you set on Discord, or do you want to go over one of the two that you set on the drive?
I think what I get a bit confused on is like drawing resonance structures, or like specifically the arrows, like, and ones that are a little bit harder, like the ones that have like 2 charges assigned to it.
Oh, right, like on this one that you sent me here, or would it be the ones that you sent me on the folder?
Whichever one is easier, like, or like easier to access.
Yeah, let me see. I have access to both here. Let's see. Oh, this Newman projection too. Okay. Yep. And this one. Okay. Oh, I see. Okay. Hybridization, drawing arrows, Newman projection, resonance groups, explanation. Okay, let's start with this one here that you sent.
Okay.
Great. Let's try to choose fill in any relevant lone pair of electrons on each compound, draw insignificant resonance structures, assign which are major, minor, or equivalent structures, draw the resonance hybrid of each structure. Okay. Right. So let's look at compound A, for example. Okay. Say you have a positive charge here, that and that. I think that's it, right? No. It's gonna be this and this. Okay, so resonance occurs between adjacent p orbitals, right? And atoms that have p orbitals are going to be either sp2 hybridized or sp hybridized.
Okay.
Right. So you have to have a network of adjacent sp2 or sp atoms in order to do resonance. If you have an sp3 atom, think of that as a roadblock for resonance. It's blocking resonance. You can't do resonance on an sp3 atom, right? But there is a scenario where you do have to worry about like pairs of electrons, right? So I'm gonna make a star here, and I go back to this this concept right here, right? But for now, let's work on this example, and then after that, let's go over the tricky scenario. So another tip for resonance that you can look out for is that arrows start from a pair of electrons or a double bond, right? Double-headed arrows. We're not talking about single-headed arrows, so we're not talking about radicals here. And go to go to a p orbital where it could be empty, a positive charge, or it could be another double bond, right? So start from a negative charge. Like another way to say is starts from negative charge and goes to positive charge. Think of it as like filling in a void, right? It starts with a negative charge and it goes to a void. Basically, it goes to something that can accept electrons. In this example right here, we see that this carbon here has a positive charge, right? Which means that it has an empty p orbital. Whenever you see a carbon with a positive charge, that is called a carbocation. And the hybridization of a carbocation is sp2 hybridized, where it has one empty p orbital, right? There's no electrons in the p orbital. So this carbocation right here has an empty p orbital like this. There's no electrons there, right? So what do you think can fill in that void, fill in this p orbital here? Which electrons can move there?
Can it go to the double bond to the left?
Yes, the double one at the left is the one that's going to be moving. Positive charges never move, right? They stay still because there's nothing to move there. It's only the negative charges that move, right? The electrons that move.
Okay.
Or the bonds that move. So the double one to the left right here is the one that's moving towards the positive charge.
Right.
Right. The positive charge doesn't move at all.
Okay.
So this double bond to the left right here is going to make a double bond right there. Right.
Oh, because it's an empty p orbital?
Yep, it's an empty p orbital. It's missing a bond. So to give it an extra bond, we can shift this double bond over to make a double bond right here, right? Which would fill in the p orbital.
Okay. So when we're doing this, like I think my initial thought is like seeing what is missing something, or like what is missing electrons.
Yep,
So,
that's the first thing you look at. What's missing electrons, right? For this example, that's what you think of, but there's other examples where there's no atoms that are like missing any electrons, right? Like for example, if you have something like this, like all the atoms here have all of its electrons. There's no empty p orbital here. Everything is full, right? Because there's no positive charge. There's no carbocation here. So you can always think of it resonance like that. It only depends on what the structure is. If the structure has a positive charge, then you look at that positive charge for that structure, right?
okay,
But yeah.
Okay, so just making sure, like if there's a negative charge, like just on the compound itself, then we know that there won't be resonance, or would we still have to double check?
Yeah, so if there's no positive charge, then there can still be resonance.
Okay.
Right. For example, if there's a negative charge, then you look at the negative charge, right? That's where you're gonna start your arrows. That's a big sign that that's where your arrows are gonna start.
Okay.
Right? So we'll do this example right after this example right here.
Okay.
Right. So we're gonna make a double bond right here, which is gonna give us this resonance structure here. And notice how this carbon lost a bond. Before it had 4 bonds, 1, 2, 3, 4. now it only has 3 bonds, 1, 2, 3. Since it's missing a bond, it's gonna have an empty p orbital. And if it has an empty p orbital, it's gonna have a positive charge on the carbon, right? Because carbon with 3 bonds is positive charge. So that's where our carbocation is now.
So when we're doing these, we're not assuming that there's hydrogens attached to them?
We are assuming that hydrogens are attached to them, but look at the original molecule here. Notice how this carbon is neutral at the original resonance structure. If this is neutral, how many invisible hydrogens are on this carbon here?
Which one is it that you're pointing at?
This one right here on the red.
We would assume that there's 1.
Yes, 1 invisible hydrogen. That's right.
Okay.
And we can't add like another invisible hydrogen. It's gonna stay as 1 invisible hydrogen like that. So there's only 1 invisible hydrogen right there.
Okay.
Right. We can't add another invisible hydrogen like that. Like that can't come out of nowhere like that. Right. And since you know that there is an invisible hydrogen right there, if you calculate the formal charge of this carbon, 4 minus 1, 2, 3, 4 minus 3 is a positive 1 charge, giving it a positive charge like that. Right? And the charges of this resonance structure is conserved. They maintain that positive 1 charge overall, net charge of positive 1. Right? What would the next resonance structure look like, do you think?
I think well, one more question. So like when we're doing resonance structures, the goal is to have it on the more electronegative atom, or like the more positive?
The goal is to move something negative charge, like a double bond or a pair of electrons, towards something that can accept electrons. And that could either be a positive charge or it could be another double bond.
Oh, right. Okay.
Right. So think of resonance as like the arrows. They start as something negative and they go towards towards something that can accept electrons, which can be a positive charge or a double bond.
Double bond. Okay.
Right.
Can we move the double bond to the one next to it? I mean, the one that has the, that one.
And make a double bond right here?
Yeah.
Yeah, we could do that. That's right. That's going to be the other resonance structure. Once I do that, what is missing here?
Is it the plus?
The plus charge, which would be on this carbon here that lost the bond. Notice how that carbon lost the bond after we did that arrow?
Right. So then that one would have a plus instead.
Yes. That's where the plus charge will be at now. Right. So these are the 3 resonance structures that they are looking for this molecule.
Okay.
Right.
That makes
sense. And if we were to draw the resonance hybrid, notice how the electrons are flowing in between like this portion of the ring, like that, like here. That's where you would put dots around that portion where the electrons are flowing at to show the resonance hybrid.
Okay.
Right? Because in reality, it doesn't stop one at a time like this. It's free flowing throughout the molecule at the same time. So electrons are flowing here constantly like that.
Oh, okay.
Right. Where you see the positive charges at those carbons will have the partial positive charge like this. Right. And that's what we call a resonance hybrid. Have you learned about hyperconjugation and the stability of carbocations yet?
Not yet.
Yeah, I see. Okay, so I'm going to give you a sneak peek of what you're going to learn ahead of time. So carbocations is what we said earlier, is a positive charge on a carbon atom. Right? A cation is a positive charge. A carbo is a thing for carbon, a name for carbon. Right? Carbo, cation. A cation on a carbon. Positive charge on a carbon. So I'm going to show you a methyl carbocation, show you a primary carbocation, show you a secondary carbocation, and show you a tertiary carbocation. And I'm gonna stop there because in 118B you're gonna learn more into like the details of this, but this is what you need to know for 118A.
Okay.
So this is what we call a methyl carbocation because the carbon with the positive charge is not attached to any other carbon.
Mm-hmm.
This is what we call a primary carbocation, which we indicate by this 1 with a degree symbol. That's a primary carbocation because the carbon with the positive charge is attached to one other carbon, like that. This is what we call a secondary carbocation. This is what we call a tertiary carbocation. And does that like make sense why it's called?
Oh, okay. Yeah, that makes sense.
Because the carbon with the positive charge is attached to 2 other carbons for secondary. For tertiary, that carbon with the positive charge is attached to 3 other carbons.
3 others. It's like sp hybridization. It's like it has 3 things attached to it.
Yeah, 3 things attached to it. All of these are actually sp2 because all of these actually has 3 things attached to it.
Yeah, because we assume the imaginary hydrogen.
Yeah, the imaginary hydrogen. Right. But the things that it's attached to is different for all of them, right? Tertiary carbocation, we think about how many other carbons it's attached to. We ignore the invisible hydrogens.
Okay.
Right. The stability of these carbocations are going to increase this way from left to right. So the more substituted or the more branched reactivity. Oh no, stability. Not reactivity. It's reactivity is the opposite direction. What the heck? Why is it? Okay. Yeah, stability is increasing from left to right. And this is due to a factor called hyperconjugation, which basically means that notice how these carbon atoms here nearby are sp3 hybridized. Those sp3 hybridized orbitals have electrons in them. Those electrons are able to donate electrons naturally, inductively, to that carbocation. And if negative charges are going towards this positive charge, is it making it more stable or less stable?
Wouldn't it be more stable because it's going towards the positive?
Yep, and opposite charges attract, right? Negative charge, positive charges attract. Like charges repel each other. So this is good. This is what they want, right? Where secondary, there's less R groups, and primary, there's only 1 R group. So think of it as like if the carbocation has more friends around it to support it, it's more stable.
Okay.
Right. Because like right now it's like missing a bond. So the more branched it is, the more substituted, the more stable it is.
Okay.
Right? So based on that factor, which one here would be our major resonance structure?
It would be would it be the third one?
The third one right here?
Oh no, it's like the top part.
The first one right here, this one?
Yeah.
Yeah, because this is tertiary carbocation. This carbocation right here is attached to 3 other carbons. 1, 2, 3, right? Whereas the other ones are attached to 2 other carbons. 1, 2, 1, 2. So this is our major resonance structure here because it has the more stable carbocation.
And we're pointing it at the one with the positive one, right? Because it has more brand or like more friends.
More R groups around it, more substitution.
Okay.
Right? Or more hyperconjugation.
And so like when we're counting, we're counting the bonds where the arrow is saying it's going to. Like if the arrow, yeah.
So there's no arrows here. This carbocation right here is bonded to 3 other carbons. 1, 2, 3. Like there's no arrows that you look at.
Oh, okay, that makes sense.
Right, because this carbon right here is attached to 2 other carbons. 1, 2. There's no arrows there. Like you could ignore the arrows here.
Oh,
right?
Okay. So
and this carbon.
So when we're saying major and minor, we're talking about like how many other carbons are attached to it, or like
how many other carbons are attached to the carbocation?
Okay.
Right. To the carbon attached to the carbon that has the positive charge. Right. If the carbocation has more carbons attached to it, it's more stable, making it major.
Okay. Is there ever a case where there's like there is no minor, or I don't know, there was a case where there was like there is no major, but you assume that it
All
can be.
equivalent?
I think so.
Yeah, there is a case that it could be all equivalent, which is going to be something like this. Where what I draw out the resonance structures out for this. All of these carbocations here are secondary. They have the same substitution, the same hyperconjugation factor. Right, and since they're all equally substituted, they're all equally major, all equivalent. There's no major resonance structure here.
So if they're all equivalent, do we just assume that they're all major instead of minor?
Yeah. We don't use the terms all major, all minor. We say all equivalent.
Okay.
Yeah, but you can think of it as all major. Right. But the direction here asks like if there's either a major, minor, or equivalent structures. In the case that I just showed you, they are equivalent structures.
Right.
Right. Like those three are equivalent structures, whereas the ones that they gave us in the practice problem, these two are equivalent structures.
Okay.
Right. But those equivalent structures are minor to this major one here.
Okay, and that's because like they all have like the same amount of carbons attached, like versus the major one has more carbons attached.
Yes, that's right. That's right. That's right.
That makes sense.
Okay. Let's see. Kathy, do you have any other questions for what I say?
Yeah, I'll send it to you on Discord.
Okay.
For that one, I was wondering like how those two are resonance of each other.
Oh, how those two are resonance? I see. Okay.
So I was trying to figure it out.
Download. Let's see. Okay. Yeah. So let's figure out the resonance structures of these here and how they are resonance structures of each other. How many pairs of electrons does this oxygen have if it has a single bond and a full formal charge of -1?
Wait, how many electron pairs?
Yes.
3?
Yes, 3 electron pairs. 1, 2, 3. Because oxygen has 6 valence electrons, but as it's drawn here, it has 1, 2, 3, 4, 5, 6, 7 electrons to itself. 6 minus 7 is -1, like that.
Okay.
Right. What about this oxygen here that is neutral and has 2 bonds right now?
2 pairs of electrons?
Yes, 2 pairs of electrons. That's right. Okay. Now, what about this carbon here with a negative charge? But before we figure that out, do you know how many invisible hydrogens are in this carbon right here? And then to figure that out, look at this carbon right here. How many invisible hydrogens are on that carbon?
On the second carbon?
On this carbon here, on the arrow.
Oh, 1.
Yes, one invisible hydrogen. That's right. So I'm just gonna draw that out to make it more clear. That one invisible hydrogen is gonna stay there, right? Does that make sense so far? Like
Yeah.
why there's one invisible hydrogen on this carbon right here?
Isn't there 2 there?
No, there's only one because we can't add another invisible hydrogen out of nowhere. Like where did this second one come from, right? Like we can't add that second hydrogen out of nowhere. It would be 2 if it's neutral, but this is not neutral.
Oh, because there's a negative charge.
Yeah, there's a negative charge on the carbon. And if there's a negative charge on the carbon, how many electron pairs are in this carbon? With 3 bonds and a negative charge.
How many electrons?
Yes, non-bonding
Um,
electrons or electron pairs.
1?
Yes, 1 electron pair, right? Because carbon has 4 valence electrons, but right now it has 1, 2, 3, 4, 5 to itself. 4 minus 5 is -1. So this carbon here has 1 pair of electrons, right? So now let's think about the resonance structures here and how we could draw the arrows that would get from this structure to this structure here. When we draw resonance structures, where does our arrow start? Like what kind of charge does our arrow start? A positive or negative charge?
Negative?
Negative charge, right? So our arrow here is going to start at this negative charge here. Do you see this negative charge on the oxygen?
Yeah.
So it's going to start there. Where do you think that that negative charge is going to go? This lone pair of electrons is going to go. Let's pick that one, for example. Where do you think this lone pair of electrons on the oxygen is going to go?
On the bond from carbon to
Yes,
oxygen?
to make a double bond right there, right?
Yeah.
Yeah, because that's going to create this double bond right here. But that's going to break the octet rule for this carbon. When we do that, that's going to give this carbon 1, 2, 3, 4, 5 bonds, right? What can we do to conserve the octet rule? What do we have to do to this bond here? Where can we move that bond?
Move it to the carbon with the
Yes.
hydrogen.
Where this bond right here has 2 electrons, those 2 electrons are going to move to that carbon, giving that carbon a pair of electrons, which is that right there.
Oh,
Right?
okay. I get it. I was just confused because it didn't like show like the carbon
Or it didn't show
and the
the
lone pairs.
pairs of electrons. Yeah. Well, it did show all the carbons. It didn't show the hydrogen and the
Oh,
pairs
yeah.
of electrons. The hydrogens and the pairs of electrons are invisible, right? That's what makes
Mhm.
it tricky here. Like they could just give you a formal charge and expect you to know how many pairs of electrons are on the atom, right?
Okay.
And they are not going to give you the hydrogens as well. You have to figure that out by looking at the original structure, and it's going to stay as that, right? You can't add another hydrogen there. If it's 1, it stays
Okay.
as 1, like that. Right?
Okay, I get it. Thank you.
And which one would be major here? Which one would be the major resonance structure?
The major one would be the negative charge on the oxygen.
Yeah,
The left
that's
one.
right. Right. Because it's more electronegative than carbon. That's right.
Yeah.
Okay. Elysia, do you want to work on another resonance problem, or do you want to work on a hybridization, Newman projection problem that you sent me?
If there's any that are like of the resonance that looks like harder to figure out, maybe one of those, and then if there's not, then something else.
Yeah, let's do compound P and R, or and T, PRT. Oh wait, there. This last row here is pretty mean. So let's do that whole last row, PQ or ST.
Okay.
Yeah, let's see. Hopefully this works. Hey, Davi.
Hello there, how are you doing?
I'm doing fine. How are you?
No, right. I don't need late, to be honest.
It's okay. It's okay. What time is it there for you again? 1 or 2?
Yeah, 1 1
2. I see. Okay.
It's always 1
Yeah. Thing. So let's say we have this molecule here. Okay. You try explaining to me what you think is gonna be the resonance structure. How would we draw that here?
I think, like we said, that we start from the negative and then we move it to the next bond over. But then if it breaks the octet, then we move that one as well to the next bond.
To make that double bond right there?
Yes.
Yes, you
Well,
can do that, but for exam purposes, they don't want to see that. They want to see you do it one at a time. So
okay.
they want you to put it on an atom instead of making another double bond to
Okay.
show that you know that you can do that. Right? But what you just said is what you're going to be doing once you learn reactions and mechanisms. But for now, they want to see you do it one at a time.
Okay.
Right? So where would this double bond go instead to show that?
It would go to the next one over.
The carbon or the atom that it's directly on right there. Right. So instead of making a double bond right here, it's going to create a pair of electrons on that carbon right there. Right. Does that make sense?
Not really.
Great. So this pair of electrons on this carbon right here is going to create a double bond right here, which breaks the octet rule. And once you break the octet rule, you have to move this double bond somewhere else.
Okay.
Right? You can move the double bond here, which is plausible, but that would break the octet rule here as well. Right? Which you have to move that double bond somewhere. And let's say that you do make a double bond right there. Where would you move this double bond right here on the right side?
I think the carbon at the end.
This one, or this one right here?
The one at the very end, like not the bottom one, but the top-ish one.
Oh, like this one right here?
Yeah.
Wait. So, we, like, are you saying like make a double bond right here like that?
Wait, 1, 2, 3. Oh, I guess you can make another bond below it, right?
Like down here, like a double bond down there?
Yeah, that one.
Wait. So, what is the hybridization of both of these carbons? Let's say the hybridization of this carbon and this carbon.
That one would be a sp3.
Yes, because there's 3 invisible hydrogens. So it has 4 bonds, sp3. Whenever you have an sp3 atom, that blocks resonance. You can't go there.
Oh, okay.
Right. So instead of making like double bonds right here, what you could do is you can. Well, first, how many electrons are in this bond right here? How many electrons are in the bond?
2.
Yeah, 2 electrons. You can move those 2 electrons and push it out to make a lone pair of electrons. Like that. So a lone pair of electrons will be on that carbon right there. Right, but that's going the shortcut route. Like that's gonna skip a lot of resonance structures. So we have to do it one at a time. Right. So we start with this lone pair of electrons here, or the negative charge, to make a double bond here. This is gonna move this double bond out and create a lone pair of electrons on this carbon right here, which is that lone pair of electrons. This lone pair of electrons came from that bond right there.
Okay.
Right. Now, this is our other resonance structure. How would you draw the last resonance structure here?
Would you grab the lone pairs and then move it over to the next carbon, and then that carbon would have lone pairs?
Right. So think of it like this. You can create lone pairs on atoms from double bonds. Right. This double bond here between these two atoms, one of the bonds here can go onto one of the carbons it's bonded to give a pair of electrons. This lone pair right here cannot jump over to give that carbon a negative charge like that. Right. We have to do something very similar to what we did originally. Right. Where we have to make a double bond first. So we're going to use this pair of electrons to make a double bond right here. Right. That's what we're going to do.
Okay.
And this bond right here, what is this bond going to do here?
It's going to want to move over.
Move over to make a pair of electrons on this carbon or make a double bond.
Pair of electrons.
Yeah, pair of electrons, that's right. Move over to make a pair of electrons on that carbon right there that it's attached to, like that.
Okay.
Right. And these are our resonance structures here, like that. Right. So the resonance hybrid would look like this. Partial negative charge here, here, and here. So the major resonance structure is going to be different than cations. The negative charge wants to be alone because we said earlier that the groups donate electrons, right? And electrons are repelling each other because they're like charges. So which one of these is the least substituted, making it the major resonance structure?
The least substituted, would it be the first one?
Yeah, it will be the first one. That's right.
Okay.
Because it's primary, this one is secondary, this is tertiary, right? We see that this tertiary one has a lot of R groups attached to it, like a lot of electrons, like into which makes it unstable because they're charges, they repel each other. Whereas the primary one only has one R group getting electrons into it, so that's less repulsion, less polarization. Right.
Okay.
Yep.
And so is that another factor to determine major that you just mentioned right now?
Yeah, that's another factor, right? Negative charge on less substituted carbon. Substituted carbon. Right. That's another factor. Right. But if you have a negative charge on a more electronegative atom versus a negative charge on a less electronegative atom, the negative charge on the more electronegative atom is going to be stable. It's going to be major. Right. But notice how in this resonance structure here, all of the negative charges are in the same atom. They're on carbon. Right. So the electronegativity is the same for all of these resonance structures.
Okay.
And since they're all the same, we have to look at the electron repulsion, the inductive effect, right? Because they're inductively donating electrons, like these hydrocarbon groups here, R groups here. Where if the negative charge is gaining more negative charge from inductive effect, then that's going to be less stable because like charges repel each other.
Can you re-explain that one more time, please?
Yeah. So do opposite charges attract or repel each other?
Opposites attract.
Yep, opposites attract. Negative like charges repel each other.
Right.
So when we have this R group right here, R groups are electron donating groups. So they donate electrons inductively, like naturally, right? Because they have electrons around their orbitals. This tertiary carb anion here, which is a carbon with a negative charge, is the most substituted, right? Where all of these R groups attached to that carb anion is donating electrons into that negative charge.
Okay.
Is that unstable or stable if electrons are going into a negative charge?
Wouldn't that make it unstable?
Yep, unstable, because negative charge near negative charges are unstable. They repel each other. If we look at the secondary carb anion right here, there's less R groups donating electrons. So which one would be more stable? The negative charge on this carbon, the secondary carbon, or the negative charge on this tertiary carbon? Which one is less stable?
The third one?
Yes. Because there's more electron repulsion here. More like charges being near each other, which increases electron repulsion, right? This primary carb anion right here is the least substituted, having the least electron repulsion, because there's only one R group donating electrons to it. So there's the least amount of electron repulsion on the primary carb anion there.
Oh, so because it's a primary, that makes it less repulsion?
Yes.
Like whereas like you said tertiary? That one has like more repulsion because there's
there's more R groups, more substitution.
More substitution, okay.
Right. More hydrocarbon chains or R groups. Like this is the important factor you need to know here. Hydrocarbon or the carbons or R groups, they are donating electrons inductively. Like that's an important thing that you need to know about this concept. Right.
So can we assume, like, since we have to draw the resonance structures, that when it comes to the last one, that one will be considered the like most unstable?
This last one would be the most unstable. That's right.
Right.
Yeah, this one will be the most unstable. This one will be the most stable, and this is in the middle, intermediate.
Right. Okay.
Right. But if, like, for example, let's say these were positive charges, right? Everything would be reversed, right? Because if they were positive charges, they prefer to have electrons, right? Because opposite charges attract. And since there's more R groups or more hyperconjugation on the tertiary carbon, this is going to be the more stable now. If this was a positive charge.
Oh, if it was positive.
Yep, if it was positive charge, then this would be the most stable major.
Oh, because the electrons are going towards the positive, meaning
because the electrons are going towards the positive. That's right.
Okay.
And that's hyperconjugation. That's hyperconjugation, and which you will learn in lecture.
Okay.
So the positive carbocation and carb anion are gonna be reversed.
Mm-hmm. Okay, that makes sense. Thank you.
Yeah, no problem. Kathy, do you have any other problems?
I was just wondering, like, is there a way to know how many resonance structures there are, like in total when they give you like a structure?
There's gonna be a lot. Like there's
Like how do you know how many
these
to
are not the only resonance structures here. These are the
Oh.
major, like relatively major resonance structures, because what you could do is give a negative charge here, give a negative charge here, positive charge there, same thing here, negative charge here, positive charge here, or negative charge here, positive charge here. But that introduces a lot of formal charges. And if you have a lot of formal charges in a structure, that's like like so unstable, we ignore that.
Oh, okay,
Basically.
so like, do they expect you to draw that too, or is it just like
No,
that's
no,
their...
no, no. Don't
Okay.
draw that. Yeah, they don't expect you to draw that.
Okay.
Right. So let's practice with another one, and I want you to determine in practice how many resin structures there will be.
Okay.
Right. Yeah, this is actually gonna be good right here. Q. Right. This is gonna be a little bit tricky because there's no formal charge here in the original structure. But let's see if you can do this. Okay. Yeah. Once you figure it out, let me know where you want to draw your first arrow, where you want to start your first arrow.
Okay. Mm. Would the first arrow be from the lone pair of the nitrogen to the bond of carbon and nitrogen?
Yes. Right. And that's good that you found that invisible pair of electrons. That's probably one of the trickiest part of this problem. But you have to figure out that there's a pair of electrons there, and we start our arrows from something negatively charged, like a pair of electrons, or from negative charge. You know that there's a pair of electrons there. We're gonna make a double bond right here. That's right. That's the first arrow. But that creates a problem. That's gonna break the octet rule for this carbon right here. So what can we do to conserve the octet rule?
Would you take one of the double bonds and put it on the carbon on the right?
One of the double bonds,
One, like, yeah.
like any one of these?
No, the one on the top right.
Yes, the one on the top right. It can't be this one or it can't be this one, right? It
Yeah.
has to be this one right here. Because you're trying to get rid of that bond since you're trying to create another bond right here. Right? So this double bond right here is going to create a pair of electrons like that. That's good. That's good. Right? You can also like make a double bond here, make a double bond there, make a double bond there, going ring around a rosy around the whole benzene ring. But that's a shortcut way that they don't want you to draw that. That's like skipping a lot of resonance structures. Right? We want to
So
draw one resonance structure at a time.
it should always go from like a bond to an atom, or like
Yes.
a lone pair of an atom to a bond?
Yes. Yes.
Okay.
A bond to an atom to create a pair of electrons on the atom, or the other way, a lone pair of electrons on the atom to make a double bond like that. Right?
Yeah.
And it can't like jump bonds too. It can't skip bonds too. You have to do it one at a time. Look at one thing at a time. Like notice how this pair of electrons here is making a double bond here, where this double bond here is creating a pair of electrons on this carbon here. It can't like jump and make a pair of electrons there, right? It has to go to that carbon right there.
Okay.
Right. That's directly on that. Which
For
is
this
going to
one, would it just be one like resonance structure?
no. There's gonna be more.
Oh, there's
Right?
more.
Right. If you create a pair of electrons here, what formal charge would this carbon have?
Oh, it would have a positive one. Is it positive?
So how are you calculating the formal charge of this carbon here?
Wait, no, that would be neutral, right?
Are there any invisible hydrogens here? And how many? Look at the original structure. How many invisible hydrogens are in the original structure?
Oh, there's one.
Yep, there's one right there. So now what would be the formal charge?
Oh, -1?
Yep, -1. So I'm gonna erase that invisible bond and draw that negative charge right there. Right? And that makes sense because we gave it an extra pair of electrons, and electrons are negatively charged like that.
Yeah.
But that does not like conserve the charges because this was neutral. This also has to be neutral. What atom has a positive charge in order to cancel out the negative charge to be neutral?
Um, how do you find the positive?
Yeah, so let's look at this nitrogen here. What would be the formal charge of this nitrogen? How many bonds are there and how many pairs of electrons are there?
Oh, okay. The nitrogen would be because there'd be four electrons attached to it, but then it should have 5.
Yes. Right. Because it lost its pair of electrons by making a double bond right there, which is this double bond right here. Right?
Yeah.
So it has 4 bonds, 0 pairs of electrons, positive charge on that nitrogen, and that conserves the charges as well because they cancel out.
Okay.
Okay, so how would you draw the next resonance structure from here?
Would you take the pair of electrons on the carbon to the right bond?
Like that?
Yeah.
Yes.
And then you would take that double bond to the carbon in the bottom?
Like this? Yep.
Yeah.
Giving that carbon what charge?
Which carbon?
This carbon that you gave a pair of electrons to.
Oh, it would be -1?
Yep, -1. Because there is one invisible hydrogen there, so it has 1, 2, 3, 4, 5 bonds, so it's 5 electrons to itself. 4 minus 5, -1 charge, like that.
Yeah.
And that still conserves the octet rule. +1, -1, 0, neutral. That's good.
Okay. And there would be another one like going to the other side?
Like this?
Yeah, and then on that, yeah.
Yep. Giving what charge to this carbon here that you're giving a pair of electrons to?
-1?
Yep, negative charge. That's right. And if you just draw a negative charge there, then you can leave the pair of electrons as invisible.
Okay.
Right? There's an invisible hydrogen on this carbon and an invisible pair of electrons on that carbon right there as well. But you have to show the formal charge clearly. Show the formal charge clearly, explicitly. Right.
And would that be the last one?
Yeah, that would be the last one, because if you were to make a double bond right here and push that double bond back into the nitrogen, it's going to go backward to the original structure.
Oh, okay.
Right, but then the double bonds are just alternated. Like the double bonds are just going to be like switched right here, right?
Yeah.
They're technically different because the double bonds are different, but you could just end there for resonance on the test.
Okay.
So there's 1, 2, 3, 4 resonance structures here. And do you know what the resonance hybrid would look like? Where are the electrons flowing in this molecule? Is it flowing all throughout the whole molecule, or is it flowing only at a portion of the molecule?
A portion?
A portion? Which portion? Like, look at the arrows. You see how here it's going all around the ring? Like the electrons here are gonna go here. They're flowing here, and they're flowing here, and they're flowing on the nitrogen as well.
Yeah.
Right. So they're gonna go all around the ring like that.
Yeah. So would it be like a dashed?
Yeah,
line all
like
over?
a dotted dash line all around the ring.
Oh, okay.
Right. In some examples, they won't do that.
Okay.
Right? Because if this was an sp3 atom, no resonance there. So there would be nothing here. Right?
Yeah.
Because there's no resonance there. But because everything was sp2, 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 or adjacent p orbitals, then the electrons are able to flow all around the ring like that. Right? Now, where would the partial charges be on this resonance hybrid? Like, where would the partial positive charge be at? What atom?
The nitrogen?
Yep, the nitrogen. That's right. Where would the partial negative charges be at on this resonance hybrid?
The negative, all the carbons?
All the carbons?
Or the carbon connected to the nitrogen?
The carbon attached to the nitrogen, this one right here.
Yeah.
So if you look at the resonance structure, that carbon attached to the nitrogen has no charge at all. It's neutral all throughout the resonance structure.
Oh, okay.
So
So
the
the carbons with the negative charge on the resonance structures?
yes. The carbons with the negative charges will have the partial negative charge.
Okay.
Right. This carbon here has no partial charge, no partial charge because it stays neutral all throughout the resonance structure, like that. Right. And the carbon attached to the nitrogen as well stays neutral as well, because there's no charge on that.
Oh, okay.
So that's gonna be the resonance structure here. No, the resonance hybrid here, right? Which one would be major? That's another type of problem that you might see. Which resonance structure is major and why?
The original one because it doesn't have any charges.
Yep. The original one because it has no formal charges. We want the minimal amount of formal charges. 0 is ideal, which is this first one here, right?
Yeah.
That's good.
And then is there like an order for each of the other ones? So like the second or second major would be like the second one?
So thinking back to what we talked about earlier, there's a positive charge on nitrogen all throughout, so that factor does not matter, right? Because it's the same all throughout, so that's equivalent.
Oh, okay.
Do negative charges on carbon want to be less substituted or more substituted? Do they want to have less groups or more groups? The carbons with the negative charges.
The carbons with the negative less?
Yeah, right. Because they want less electron repulsion, right? They want less electrons being donated to it. Whereas positive charges, like the positive charges on the carbon, they want to be more substituted because there's more electrons like stabilizing that positive charge. Does that make sense?
Yeah, that makes sense.
Right. But the negative charges, they don't want any more electrons because like charges repel each other. So all of these carbons here with the negative charge, notice how they're only attached to 2 other carbons. Like all the carbons with the negative charge, they're attached to 2 other carbons.
Yeah.
That's making them a secondary carbon anion. They're all equally substituted. So all of these are equivalent resonance structure.
Okay. That makes sense. Thank you.
No problem. Okay, so that's the end of the office hours. I hope that helped. Do you guys have any last minute questions?
I just have a short question with the one that you were working on just now.
Yeah.
So you're saying that the ones with the negatives, those were like, they don't, or they're like the least substituted because they're negative already, so they're going to repel each other. Whereas like, let's say the N, it's positive, so it's going to want to attract the negatives.
Oh, okay, yeah. Since you said that, there is gonna be something that's major here, and there's something gonna be that's minor here. 2 of these are gonna be equal, where the 2 of them are gonna be major over the one of them, right? So, like you said, opposite charges attract, right? Like positive, negative charges attract. So they want to be close to each other as possible. This one here and this one here, down circling, those 2 are gonna be more stable than this one right here, right? Because the opposite charges are closer to each other, right? They are attracting each other. Whereas the one in the middle, notice how the positive charge and the negative charges are on the opposite side. They're the furthest away from each other, far away from each other. That makes it the least stable, right? Because since opposite charges attract, we want them close to each other. The distance between these are the closest, whereas the distance between the opposite charges here are the farthest.
Oh, okay. So you said because the opposite charges are the farthest, that makes it less stable?
Yeah. Because the opposite charges, they want to be
because they want to come close to each other because they would attract. Oh,
yes. Yes. Right.
Okay.
Where where they are the closest here and here. That's right. That's right. Thanks for bringing it up.
Does that have
that's
anything? Sorry.
Yeah. Sorry.
Does that have anything to do with like the idea of like staggered and eclipse or
Oh
no?
no. That's a separate concept. That's talking about Newman projections, staggered eclipse, gauche confirmation, anti-confirmation. Yeah, that's something else. Torsional strain, steric hindrance. That's something else.
Okay, and so just to make sure, those two that you pointed out, they're more stable compared to the middle one, but they're not major.
Yes. If I were to rank them in order of stability, the number one major one is that one, and then these would have the same rank of number two, and this would be the third one right there.
Okay, that makes sense. Thank you so much.
Yeah, no problem. Yeah. So that there's a lot of resonance factors here. But do you guys know the number one important factor for resonance to determine the range or structure? Like, what's the number one factor?
No charges, zero is ideal.
Is it?
So that's the second. That's the second one. Huh? All atoms want to have what rule?
Octet.
Octet rule, right? All atoms want to have 8 electrons, except hydrogen. Hydrogen is 2 electrons. Yeah.
And then you said one more thing that we know that there are more resonance structures when we don't like come across an sp3.
Yes.
Okay.
When you come across an sp3, you stop. You can't make anything there. You can't make a double bond there. You can't give it that negative charge. When you see an sp3 atom, you stop.
Okay, that makes sense.
There's one exception here, because what would be the hybridization of this nitrogen here? And a pair of electrons counts as a group. So if this nitrogen has 3 bonds and a pair of electrons, what would be the hybridization of that nitrogen right there?
Is it sp3?
Yes, sp3. That's right. 4 bonding groups, sp3. But now, if I put a carbonyl double bond nearby there, this nitrogen here looks sp3 because it looks like it has 4 bonding groups, right? 1, 2, 3, 4. But it's not actually sp3 because it could do resonance with the carbonyl to get this resonance structure here. Where now, notice how it's now sp2 because it has 3 bonding groups. 1, 2, 3. This nitrogen here is going to prefer to be in the sp2 hybrid orbital over the sp3 orbital to allow for resonance. And resonance increases the stability of the molecule, right? So in order for this nitrogen to do resonance, it has to be in the sp2 orbital, right? So this nitrogen here is sp3. This nitrogen here is sp2, right? So keep that in mind.
Okay.
If the nitrogen with the pair of electrons can do resonance, it's sp2. If a nitrogen with a pair of electrons that cannot do resonance, it stays as sp3. That's the tricky thing that I mentioned earlier at the beginning of the session. Okay. So this is going to be like one of the trickiest concepts here for the resonance quiz.
And is that something that we should know as in A already?
Oh, as an Na?
Like in A, like 118A?
Oh, yes. This is something you should know in 118A.
Okay.
Your TA like should go over it, or professor should go over it, but it is like in the discussion manual. Like as you do the practice problems, there's a lot, but there is something like this on the discussion manual, which would like most likely show up in the quiz. It showed up for Leaven's quiz and the series quiz all the time.
Okay, thank you so much.
Yeah, no problem. Okay. I'll see you guys tomorrow. I hope this session helped, and good luck on your quiz this week if you guys haven't had it already. No problem. Okay. Long day. Hello.
Hello.
Lol.
How was your guys' day today?
It was alright, to be honest.
It was all right. Yeah.
I'm dead
Yeah.
tired.
Getting tired.
Yeah, I talked about like willpower yesterday.
Uh-huh.
It's just not hitting for me today.
It's not hitting for you today? It's hard to keep that willpower?
It's hard.
Oh shoot.
Uh,
Dang.
I talked about like, excitement in like the subject I was studying, but like
Uh-huh.
I don't know. I gotta do like a presentation in school. I'm just like,
Right.
and I don't feel like it.
Dang. Were you guys able to like follow along in today's like office hours? Like, did it make sense? Because it's like kind of general chemistry stuff as well.
Well,
I came really late.
Oh yeah.
I mean, I've not been on the office hour that much recently. I'm trying to stay more on the office hours now. Just
Yeah. I
just
see.
coming more frequently.
More frequently?
Yeah, more frequently to office hours.
Yeah, that's good. That's good.
No.
Now they're learning the beginning of organic chemistry, which is a little bit of a review of the end of general chemistry. You know, so it's gonna be good when you guys learn about like AP Chem, Gen Chem in college, or like high school chem. Yeah.
Nice.
Yeah. What time did you guys wake up today?
I think I like 11 a.m. 11 a.m.
11 a.m.
Yeah.
What about you, Ryan?
7. I just went back to sleep. I think like today I would like try to like instead of like shutting off my alarm, I'll shut off my alarm, turn on my I already turned on my computer. I just forgot to like wake up. Like I just was still on the bed. So
Oh.
I'm gonna like turn on my computer and I'm gonna then go outside my room and brush my teeth and then
Uh-huh.
maybe that'll wake me up.
Oh yeah. So you couldn't wake up at like 4 like you planned last night?
I can't.
Yeah. Like, did you wake up at 4 though? And then you're like, screw that, let me go back to sleep.
Yeah, my brain wasn't working.
Yeah, that's fine. That's fine. Prioritize your sleep and health, you know. But if you are able to like wake up and be focused at that time, then you could use that to your advantage and do work that time if you can wake up, you know.
Uh-huh.
Yeah. Yeah, this week's your final week, right? Like you have a final this Thursday.
Uh-huh. Wait, what?
Yeah. Like you have a final exam this Thursday.
Thursday, Friday.
Thursday, Friday. Yeah. Good luck. Good luck. Are you feeling more prepared? Much more prepared for it?
I'm so tired.
Oh shoot. It's been a long day for you, huh?
Mm-hmm.
Yeah. Dang. Okay. Yeah. So let's catch up tomorrow at Alpha Stars again, and Sunday we have a study session with me again, 3 to 6 p.m. and also like that talking session with no like organic chemistry, no tutoring, 9 to 10 p.m. on Sunday. It's
That
on the
sounds good.
calendar. Yeah.
Mm-hmm.
Yeah. Okay, so I'm gonna let you guys go, and good night.
Good night.
All right. Good night for you too.
Yep.
Good night.
Bye-bye.
Bye-bye.
Bye.
Bye.